Hello to everyone and welcome on the YouTube channel School for All. I'm called Paula Eve, the computer science and ICT teacher and also the CEO of School for All. So today we are going to answer one more question on logic gate. So I've chosen a question under full adder and half adder. So this question is under June 23, question 1B, Roman 2. Now, so many students are texting me concerning this type of question, full adders, half adders, I'm not understanding, and so on and so forth. So what will happen in this video, as usual, I'm going to explain first of all where half adder and full adders are coming from, so that you understand exactly why you are studying them. I'm going to briefly summarize, in fact, the meaning of each before we answer the question. Very, very important. Now, so yeah, when we talk about half adder and full adder, we are at the level of digital circuit. We are at the level of digital circuit. This is what you need to know. And we talk about digital circuit, we are talking about what combination of gates, because yeah, I'm not starting from zero logic gate. No, I'm assuming that you know type of gate, and gate, or gate, and all these things. Now, so what happens here? I'm at the level of digital circuit, and we know digital circuit generally a combination of gates that work together to produce what output. But you need to understand that we have two types of digital circuit. There's what we call combinational logic circuit, combinational, and that's what we call sequential. Either you say sequential digital circuit or sequential logic circuit. Very important. Now, after knowing that we have two types of digital circuit, you need to know the definition of each, because there are some past questions where they are asking it. Now, sometimes students, when they are defining things, even to start a definition is a problem. So it's not difficult. Since you know that a combinational logic circuit is a digital circuit, or a sequential logic circuit is a digital circuit, you can start your definition by saying that it is a digital circuit before you move. Now let me start with combinational logic circuit. So you start your definition by saying this: it is a digital circuit. I'm not writing everything as usual. You know, you pause the video, you take a notebook and you note what I'm saying. It is a digital it is a digital circuit. Now when we talk about digital circuit are just combination of gates that work together to produce an output. So then to start their definition by repeating that it is a combination of logic gate that produces an output based on input things like that, no, it's too long. So you can just say it is a digital circuit whose output depends on the present inputs. Very, very important. A digital circuit whose output depends only on the present input. Meaning what is very important here, you need to know that this is time independent. Good. And you need to know also that here is what? There is no memory. I'm giving this one especially for paper 1 where they are asking this type of question. Now, time independent here simply means what? That it is not depending on a history output. Meaning that when you are producing your output is based on the actual input you have. It's not as if your output is based maybe on the answer of the previous operation. No, there's nothing like that. And if it's time independent, it's simply that it requires no memory, because the memory generally is used to store a value, and that value will be used in another operation. So yeah, there's nothing like that. So I'm going to take an example. Example here is what we call adders, binary adders. Good. If I take something like 1 plus 0, the answer is what? The output is 1. So you are seeing that this answer here depends only on the present input. If I take another example, 1 plus 0, something like that, it's going to make what? 1 plus 0, which is a 0 and carry 1. You bring down the 1 here. So you are seeing that the output depends only on the present input. So this is exactly what we mean by combinational logic circuit. Now for you to get it very well, let us go to sequential circuit. So the same thing, you start by saying that it is a digital circuit where, or you say it's a digital circuit whose output depends on the present input and history output. I think we are seeing the difference here. Here, the output depends on the present input and history output, meaning that the previous output. Examples here, we have counters. Imagine that you have something like this: A is equals to 1. Then you come and do A equals to A plus 1. So this one operation here, or let me just say initially this is what we have. The first operation, you will say A equals to A plus 1. What happens? You take this one, you come and put A plus 1. It makes what? It makes, so A becomes what? A becomes so. Imagine that the next operation is A equals to A plus 1 again. What happens here is you are going to take the previous value of A, meaning this previous value is a history output, meaning it's a previous output. That output is what you are putting here to sum. And generally, you have counters work because a counter must start. Let us say I even started at 1. It's just an example. Generally, when you are doing programming and you want to count something, you always have a variable starting at 0. Then you'll be doing what? 0 plus 1 plus 2 plus 3 plus 4. So you are seeing that you are adding new input to previous output. In fact, that's why here you are seeing that the output depends on the present input and the history output. So in this case, the present input is this one that you are always adding, and the history output is what is the previous value of A, and the previous value of A is the output of another operation. I think I'm very clear. So combinational logic circuit output depends only on the present input. Sequential logic circuit, a digital circuit where the output depends on the present input and history output. So I think we are clear. Now, so generally advanced level, we are not focusing on sequential logic circuit. No, we are concentrating but on combinational logic circuit. Now, we have different type of combinational logic circuit, but the most important one for you people in advanced level doing computer science is arithmetic and logic circuit. So this is what you are doing there. So when we talk about, so let me just clean everything. So note that here we are focusing on combinational. Let me take another book marker. Here we are focusing on combinational logic circuit. Good. And we have different types. The one we are going to study together is what we call arithmetic and logic circuit. Good. Take note of things like that, please. We are going to study arithmetic and logic circuit. And under arithmetic and logic circuit, we have different types. Very important. This is what we call binary adders. This is what we call binary subtractor. And the last one is what we call binary comparators. Good. And all these things, you must know them. Very, very important. So for today, the question that we are answering is under binary adders. So we are going to focus only on this part. I think there's Southwest Mock 2025 or 26, something like that, where there's a question under binary subtractor. So if you need this video, please just leave comments. So from your comments, I'm going to see if it's interesting, and from there I will do more videos. Binary comparator, there's also another part here like that. In fact, if you need videos on this, just leave a comment, please. And before starting this video, make sure you like the video. Very important. If you have not yet subscribed to the channel, subscribe to the channel. Good. You're not paying to look this video, so this is the minimum you can do. Now, so we are done with this. Let us concentrate now on binary adders. So what's binary adder? So the definition is also very easy. As you know, binary adder is a type of what? Arithmetic circuit. So since you know it's a type of arithmetic and logic circuit, you start by saying that it is an arithmetic circuit before you continue. As I'm always telling my students, it's very easy. So what you need to know here is that a binary adder is an arithmetic logic circuit, or you say an arithmetic circuit used to add two or more binary numbers. When we talk about binary numbers, we are talking about 0 and 1. So a binary adder is just used to add 2-bit numbers or more than 2-bit numbers. Take note. So if you're adding something like this, 1 plus 1, you need the addition of what? 2-bit numbers. If you add something like 1 plus 1 plus 1, this 3-bit number. So the whole of a binary adder is to add 2 or more binary numbers. Full stop. Now, under binary adders, we have 2 types. So we are coming exactly to our question. So the 2 types here, we have half adders, and we have what? Full adders. So this is exactly where half adder and full adder is coming from. I think you are seeing the path. Very, very important, because I don't really like when someone is studying something without even knowing where it's coming from and so on. You forget very fast. That one is normal. Now, what's half adder? What is full adder? Half adder, let us start here. Half adder is a binary adder. So this is how you start your definition. A half adder is a binary adder. Someone can also start by saying that a half adder is a combinational logic circuit. There's no problem. It's still correct. Or you say a half adder is an arithmetic circuit that will continue. There's no problem. So let us continue. A half adder is a binary adder used to add 2 input bits, in brackets say, let us say A and B. So we are calling the first bit A, the second bit B. So it is a binary adder used to add 2 input bits, say A and B, and produce 2 outputs, sum and carry. So this is how we call the output here. The output here is called sum, and the other is called carry. So the definition is clear. It's a binary adder used to add 2 input bits, say A and B, and produce 2 outputs, so called sum and carry. So the next thing generally is to draw a truth table with 2 input A, B. You fill your different input A and B, and the next column you write the sum, the next column you write carry, then you fill the truth table. So I'm not doing that one in this video because the aim of this video is just to answer this past question. If I want to do so, I'm going to waste time. So please, any problem here, just leave a comment. Yeah, we can discuss about that. So this is a half adder. What's a full adder? Now, you need to understand something. That full adder has been created to solve the problem of half adder. Half adder can only sum 2 inputs, whereas there are some situations where we need to sum the 3 inputs. In that case, half adder cannot handle that one. We need to add a full adder. Let me just take an example for you to understand. If I have something like 1 plus 1, something like that, or 1 plus 0 or 0 plus 0, we are seeing that this is what a half adder can handle this situation because we just have how many inputs? 2 inputs. So the half adder can just sum it. 1 plus 1 is what? 0, and carry 1, then you bring down the 1. It's clear. But imagine that you have this situation where you are having something like 1 0 1 plus maybe 0 1 1. Okay, so the first addition here, you have what? 1 plus 1. Half adder can handle 2 input, no problem. The answer is what? 0 and carry 1. But the next addition is what? 1 plus 0 plus 1. 3 inputs. So in this case now we need what? Full adder. So this is exactly how the full adder comes in. So let us define what is full adder. So yeah, full adder, the same thing. A full adder is a binary adder used. So let me just write it somewhere here. I hope you will see. Good. Let me just take another marker. A full adder is a binary adder used to add 3 input bits. Input bits. Used to add 3 input bits. Say now the 3 input bits here, you say A, comma B and C in. The third input bit here, we call it C in. C in simply means carry in. I'm going to explain the meaning of that if you're not understanding. So you also add 3 input bits, say A, B, and C in, and produce 2 outputs called sum and C out. Good. So C out here means carry out. C in means carry in. Like here we are just having a carry out. That's why we just say carry, no problem. There's nothing as carry in. That's why we don't precise which carry here. But yes, since there's a carry in and a carry out, that's why it's very important to mention C out here and yes C in. If you just say carry here, it's a little bit confusing. Now, so let me just explain this one. As I was telling you, if I'm having something like this, 1 0 1 plus maybe 0 1 1. If you do 1 plus 1, half adder, no problem. You have what? 0 and carry 1. So what you are carrying here is what we call a carry in. Carry in simply because another operation will be taking this as input to perform its own operation. That's why you are seeing here. The next is what? 1 plus 0 plus 1. So the 0 that you are having here is this A. The one that you are having here is this B. Now the other one up here is what? The carry in. So that's why we talk about what? Summing of 3 inputs. I think I'm very clear with this one. Very nice. So I think after explaining this, the next thing also is the same thing here, drawing a truth table with 3 input A, B, C, then filling sum and carry out. So this one, if you have problems there, we can discuss later. So after drawing this truth table, you need to know also how to draw the circuit diagram of half adder and full adder. You need to know what is the Boolean expression of sum in half adder, the Boolean expression of carry in half adder. What is the Boolean expression of sum in full adder and the Boolean expression of C out in full adder. These are questions that they ask in the GC. So don't play with it. I mean, when you're studying that, make sure you know it. If you have difficulties on that, I can make more videos. But as I was telling you, the aim of today is just to answer a question on June 2023. So I think with this summary, we are very clear. So if I want to summarize back, make sure you know that all what we are doing is following on a digital circuit, meaning a combination of different gates that work together to produce an output. Now, on a digital circuit, we have 2 types: combinational logic circuit and digital logic circuit. So I've explained that already. Now, after knowing that, the next thing that you're supposed to retain here is knowing that we have different types of combinational logic circuits, but what people study in advanced level is what? Arithmetic logic circuit. Arithmetic logic circuit is divided into how many? 3 types. Binary adder, binary subtractor, and binary comparators. And for today, since we are answering a particular question, we focus on binary adder, which is also divided into what? Half adder, full adder. Make sure you know the differences between what? Half adder and full adder. Nice. So let us go to a question. So let me just, okay, where's that question? I think I have it somewhere here. Okay. So let me clean this. So make sure you pause the video and you copy. Now, so the question is question 1, B Roman 2. You see, good. Now, the B Roman 1 is under computer architecture. So I think I did a video already on the YouTube channel explaining everything on computer architecture. So any problem on that chapter, go and watch the video. Now, if you have any problem to find the video, my contact is in the description of the video. You contact me, I will just send you the link directly. So there's no problem there. So we concentrate on Roman 2. This is what the question is saying. They say we want to build a circuit that can be used to add 2 4-bit numbers, full stop. we have full adders and half adders to use as components. So it's very clear. So the question is saying that you are trying to build a circuit used to add 4-bit numbers. So I'm going to show you how to do so. Yeah, and that you're supposed to use what half adder and full adder. Now, so this is the idea, because there are some questions that they can just enumerate like that and they ask you to draw the circuit directly. If they ask you to draw this circuit, so 4-bit, yes, so long. Let me just take the case of 3 bits. Now, if they're asking, or let us say 2-bit, yes, to make it very short. If they ask you to draw a circuit used to sum 2-bit numbers, like I think they always more they add something they ask something like that, 2-bit numbers. Good. In this type of situation, you will say let the 2-bit numbers be, you call it maybe A1, A0, and B1, B0. Now, why is that I'm saying A1, A0 and not A0, A1? Simply because generally when we are doing binary addition, if I have something like this, example, e.g., if I have something like, let me take another marker. Example, if I take something like this, 1, 0 plus 1, 1. So what happens generally when you are doing your addition, you are starting with what? With the least significant bit, meaning you are starting from right to left. So writing something like this simply because I want to represent this. I want to write something like A1, A0, B1, B0. So just to tell you that we are starting with what? The 0 here for me is like saying the least significant bit, you see. And the biggest number on this side, I'm taking it as my most significant bit, so I'm writing it like this, taking note of things like that. Now, after doing this addition, what happens here? You have what? A0 plus B0. Let me just call the output here to be S0. A1 plus B1, let me call the output here to be S1, something like that. Now, generally what happens here, when you're drawing this circuit, the first component here should be the half adder. So this half adder is represented because the half adder normally is made up of multiple gates, you see. Good. So this how we summarize it. The same thing, full adder we summarize, you are just drawing a square and you just write full adder inside. And how are we representing it? Generally, you have 2 arrows up there. These 2 arrows represent the input. So my first input is what? A0 plus B0, and the output is represented down here. What is the output? S0, you see. Now, generally, the carry in is represented on this side, and we know that half adder cannot have carry in. That is why there is no arrow here. Take note of things like that. Now, so after doing this first operation, the next operation here, normally there is a carry in. Just that if here is maybe, I don't know, 0 plus 1, the output will be what? 1. In that case, you just take your carry in as what? As 0. If you're having 1 plus 1, the output will be what? 0, and the carry will be what? 1. So here, let us assume that there's a carry called maybe C0. If there's a carry, it simply means that the next person here should be what? Should be a full adder. That full adder is adding what? It's adding first input called A1, second input called what? B1, and it's producing what? A sum. So here's what here. Let me call that S1. And the last one here, let me just call it C out. Because when you are having full adder, you must always produce what? Sum and carry out. Even half adder, you must also always produce what? The sum and carry. Good. And this carry here become the carry in of this full adder. Take note of things like that. And in this case now, if your carry here can be 0 or 1, so we know that already. Now, how to take the answer? Generally, the answer is being taken by doing this. Sum is equal to, you take the carry out, C out, you join it with S1, you join it with S0, so you're taking the answer like this. Take note of that, very, very important. So this is the case where they ask you to draw a circuit by precising the number of bits of your input. It's all, without giving you any value. But this question is not the case, but I'm doing this one because there are some questions that they ask it like that. So any problem here, please ask in the comment section. I think I'm clear. But if you have any problem here, I will answer the next question, you will still understand it. So don't worry. Now, let us continue with our question. You should get it very well. Now, they say explain the difference between half adders and full adders. So I don't want to repeat myself. I think people have noted what I was saying here at the beginning. So that question is clear. We go to B. They say draw block diagram circuit which shows how the number 1011 and 1110 are being added. So we are drawing a circuit showing how these are being added. Full stop. They say show and label all inputs and output. Full stop. Use at least one half adder and full adder. So very, very important. So the technique to solve this type of question is clear, dear students. So you will start by doing a normal binary addition. Normal binary addition is what? You will have something like 1, 0, 1, 1 plus what? Plus 1, 1, 1, 0. So let us do normal binary addition. Here we are having 1 plus 0 is what? Is 1. 1 plus 1 is, now this one here, you are seeing that this one here is your sum. Normally the carry here is what? Is 0. Take note of that, please. This is half adder here. 1 plus 0 is what? Is the sum of two inputs, and this is what half adder. And half adder produce what? Sum and carry. And what's the sum here? The sum is 1. It means that the carry automatically should be what? 0. Good. Now, you take this one. 0 plus 1 plus 1. So this is already what? Full adders, because you are adding what? You are adding two input A, B plus a carry in. So what will be the answer of this operation? 0 plus 1 plus 1 is the same as 1 plus 1, which is giving you what? 0 and carry 1. So you write your 0 here. You write your 0 here. And you carry 1. Now 1 plus 0 plus 1 is still 0 and carry 1. 1 plus 1 plus 1 is what? 1 and carry 1. You bring down the 1. This is a final answer. So do it like that first before you start drawing down what? The secret. Take note of that. Now, the secret, generally, the first component here should be what? Remember, the half adder. Sorry, half adder. Taking which input? First input here is what? Is 1. You write your 1 directly. The second is what? Is 0. You write 0 directly. What is the output? The output is 1, right? You write your output down here 1. Good. And what's the carry? The carry is 0. Now, so you are seeing that the next operation now, we are using a carry. So this is what a full adder. So use full adder. So just put in mind that generally it's only the first component that is half adder and the rest are full adder. Take note of things like that. Now, it's also possible that the first here should be a full adder. I'm coming there. Let us answer the question first. So here you write what? Full adder. What is the first input of the full adder? The first input here is not that 0. No, that 0 is the what? The carry in. The first input here is what? Is 1. Second input is what? Is 1. Good. And the answer is what? 0. 0 and the carry here is what? 1. You draw and then you write your 1. So there's some generally this is a technique I'm showing my students, because when you do like this, it becomes very easy to see and just come and draw. Even though you can draw it directly without even doing it. It's just a technique that I've created for my students. Now, the next here is what? Full adder. Full adder. So yeah, full adder between what and what? So this is 1, 0, 1. But this one here is a carry in. Take note. So the first input here is what? 0. So you draw like this. You write 0. The next is what? 1. You draw here. You are 1. Take note of things like that. And what is the output? The output here is what? Is 0. And the carry is what? The carry is 1. You write it here. Now you draw another full adder. This full adder here. Good. When you draw this next full adder, the input here is what? A, which is 1. The next is what? Is also 1. And the carry in object is 1. We have resized it already here. Good. So what is the output? The output here is what? Is 1. And the C out. This last input here is the C out, right? It is what? It is 1. Good. So now what is the final answer? The final answer, what did I say? That we take the last C out here, which is 1, combined with all the sum that we have down here. So it's 1. Then you take this other. You take this 1 first. Then you come and take this 1. Then you come and take what? 0. Then you come and take what? This 0 also. You come and take what? This 1 also. Good. At the end, this is your final answer. If you look very well, this and this, they are the same. Meaning this is secret you also perform this operation. So I think it's very easy. So as I'm always telling my students, there's nothing behind all this. You just need the right explanation and everything will be flowing normally. Now, and this is called parallel secret. So when they ask you to draw parallel secret, they are talking about things like that. Either we call it parallel secret or we call it ripple like this. Good. Ripple secret. So take note of things like that. So these are also some few names you may see on your paper. So take note of that. Now, the next thing is, imagine that the question asks us to draw this secret using full adders only. If they say using full adders only, it simply means that here I'm not supposed to have half adder, you see. You remove this, you put what here? Full adder. But if you put full adder, you leave it like that, there's a problem. Because normally we know that a full adder requires what? A carry in, right? So in that case, if you put full adder here, just come and add an arrow here like this. And this arrow automatically should be what? Should be 0. Good. So that it should not affect. If you put 0 here, it's as if you're just adding a 0 here, and 0 plus 1 plus 0 is to give you that one. So this is the case where they ask you to draw using only full adders. Good. But generally they will ask you to combine. So let me just clean this and this back at things the way it was. So half adder. So we are done. So let me just look if there's something else. It's all. So the Roman trade say describe characteristic of CPU is still under computer architect. So okay, so we are done with the tutorial. So if you have enjoyed the video, make sure you like the video, leave a positive comment. Any problem, drop in the comment section. I will reply to you. My contact is there. Ciao. So make sure you share the video to your friends. Bye bye.